Alright, you are here for 4.1 Graphs of Polynomials. Basically, this is the first section in Unit 4. Unit 4 talks about only polynomials. We're going to get to some graphs, some multiplication, some division, some writing polynomial functions in this particular unit. But we're going to start off with some graphing. And we're going to need our calculator, so that Wabbit calculator that I sent you guys, you're going to need to make sure that's opened, not for the first page or so, but for the last couple examples in our notes, you're going to need that Wabbit calculator. And I'll go through how to open that up and talk about how to use it and so on and so forth throughout the video and the subsequent videos as well. So first off, to graph, what we need to understand four main ideas. So the four main ideas that we're going to need is what a polynomial function is. So what a polynomial function, if you write small enough, you'll be able to figure it in there. I don't write small enough, so that's why it's there. What a polynomial function is, we'll get to that down here as well. Number two, what extrema are. It talks about minimum and maximum. Again, we'll get to what that actually means down below. Number three, what end behavior is. Okay, so what end behavior is. Again, end behavior, we'll get to it, but end, I mean, we'll talk about what the ends are, but that's kind of like the outer edges of the graph, and what actually happens at the outer edges. So end behavior is what happens at the outer edge. That's basically what we're talking about there, and we'll give some examples. And then number four, what are the roots, x-intercepts, and zeros are. Now remember, we also had another name for this, it's called solutions. Okay, so roots, x-intercepts, zeros, those are the main primary ones, but solutions also comes into play as well. Alright, so we have three, these are interchangeable, so I can use all four of those and they mean the same thing. So now let's get into actual what a polynomial function is. So a polynomial function is a function of this form. F of x, that just means, so f is the name of the function, x is the variable that's in the actual problem. So it says ax to the n plus bx to the n minus 1, and so on and so on. And these dots means it goes forever, 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 right? So on and on and on and on, until we get to a number at the end that has no variable. Technically, it does have a variable, right? It's really x to the 0 power, but anything to the 0 power is 1, so that's why there's really no variable that needs to be written. So this is what happens. It starts off high, so this is the highest number, and then it gets minus 1, minus 2, minus 3, all the way down. Now you could be missing some numbers. It doesn't have to be in, for the most part, numerical order, greatest to least, but it always starts with the highest. Well, what happens? Where a is called the leading coefficient, and then n is called the degree. Now, leading coefficient, that basically says, if I look at the highest term, or the highest degree here, which is n in this case, the coefficient is the number out front. That's the leading term. It doesn't matter if ax to the n is way down here or way at the end. It's still the leading coefficient because the highest degree is what I always want. It always goes greatest to least. So it doesn't matter if it's over here. I technically would have to move it and make sure it's least or greatest to least. Okay? So here's an example of what I'm talking about. So if I have this example, f of x equals 3x squared, I'm sorry, 3x to the negative 2 power plus x to the 5th power. You would see that this 5 is actually the biggest one. Okay, so we would change this and say x to the 5 plus 3x to the negative 2. But what this polynomial function says is I cannot have x's in a denominator. Okay, my variables, my exponent of my variables have to be a positive number. This is x to the 0, and that's where it stops, remember? It doesn't go negative 1, negative 2. Because what would actually happen was this would be 3 over x squared. And this is a fraction, and there's no fractions that talk about that up here. So this wouldn't be a polynomial function. I'm just letting you know that we could rewrite it that way. But it wouldn't be one because x squared's in the denominator. What are some other examples? Well, x to the negative 3 power, again, that's not a polynomial function because that would be 1 over x to the 3. That's in the denominator. But what about this? What if I had a number raised to a power, x? Well, there's nothing in here where x is in my exponents. X is the base of your polynomial function. It has to be in the base. It can't be in an exponent, and it can't be in a denominator. These are not polynomial functions. These are. This is what every one of them looks like. Now, when a function is written with terms in descending order, means greatest to least. Greatest to least. We say that the function is in standard form. Remember we talked about standard form before? We talked about standard form of linear equations when I said it was ax plus by equals c. All the x's and y's are on one side. So that's standard form in linear equation. This is standard form in a polynomial equation. Okay, a polynomial function there. For some reason I put this there twice. You don't need to do it twice unless you really want to write it down twice. That's up to you. I wouldn't choose to, but again, it's your call. So let's scroll down a little bit. Okay, we decide whether the function is a polynomial function and state its degree and leading coefficient. So what's going to happen is I want to first make sure it's a polynomial function. So is it yes or no? So this is a yes or a no type question. If it's a yes, I'm going to go on and state its degree and its leading coefficient. Okay, I don't have to go further if it's no because I don't have any of them, right? It's not a polynomial function. So first I want to put it in standard form. So because that 5 is bigger, I have to move it out front. So negative 4p to the 5 plus 2p to the 3. Now I need to make sure it's an actual polynomial function. Are all of these degrees positive? 5 and 4 and whatever what else was there, are they positive? Yes. Does the p make it, is it a p in the denominator or is there a p in a exponent? No, of course not. So this is a polynomial function. Now I need to find its degree and leading coefficient. So degree, it's the highest one. So 5 is the highest one. And then because that's the 5, what's the coefficient in front of the p? Well, that's negative 4. So that's the degree, leading coefficient. Let's go on to the second one. If I look here, I can automatically tell me that this is not a polynomial function. The reason why is this looks good and this looks good. And you're like, yeah, but no, because this x is in the denominator. That doesn't matter. That doesn't count for a polynomial function. So it is a no. You'll learn more about that later on. That's what we call a rational function, and those graphs look very different. The third one over here, are these positive? Yes. Do I have any x's in the denominator or any exponent? No. So this is a polynomial function, but I need to order it correctly. So this is negative x to the 5th minus 3x squared. So now the degree is the highest, so that's 5. What's the leading coefficient? Well, that's the number in front of that highest degree, which is actually a negative 1. So there you go there. Now let's start getting into some graphing polynomials. So the graph of a polynomial function is always a smooth curve. It has to be smooth. Okay, has to be. That is, it has no breaks or corners. So if we look at these two, this is a break. And what I mean by that is this. If I take my pencil and I'm drawn, and I come to that, I have to lift my pencil up in order to continue. So then I have to lift it up, move, and then continue. And then I really got to lift it up here because there's a hole. Okay, you'll fall into a hole. You ever seen that movie with Shia LaBeouf and I don't know who that dude is, but they're digging holes in the desert and they're gonna fall in and starve, I guess. I don't know, but there's a hole right there. So then I got to lift it up, and then I got to keep going. Okay, because of this break. Okay, so these graphs are not polynomial graphs. Well, because that one's not, right? But this one here, if I look, this really comes to a point. Okay, and what it looks to be a corner. So the reason we got corners here, we got what we call cusp. We don't need to know the actual definitions of that. That's later on, but that's what happens. We comes to a point. If you'll notice, these two graphs over here are smooth and continuous, like a baby's bottom, right? Well, continuous, that would be kind of bad, but they are pretty smooth. We got this. It goes on and on and on. It's really nice and smooth. I'm not picking up my pencil. That's what makes it continuous. I don't do any of that stuff. So I can just graph this right from here. It's got nice little smooth little action going on. Same thing here. This is pretty nice and smooth, and so on, and I finish it. Smooth and continuous. Continuous just means you don't pick up your pencil at all. So these graphs are polynomial graphs. All right, let's come down to some fun extrema and roots. So some awesome stuff here. Yeah. So extrema. We have a couple different types of extrema. Okay, one is we have a whole bunch of maximums. We have some minimums. Remember we talked about these before when we talked about graphing quadratics, where if I had a quadratic graph that looked like this, that means this would be the minimum. If I had a quadratic that looked like this would be the maximum. Well, that's pretty similar to what we're doing here, but in polynomial functions, we might have a couple more max and mins. Because of the graph, it doesn't look like a U, it kind of looks like a weird little snake going on over here. So this is just an example of a graph. They look different than this as well. So this is just one example. So in each maximum minimum, we have what we call an absolute maximum and what we call a relative or a local. So these two are the same, okay? They mean the same thing. So again, they're interchangeable. An absolute maximum is within the whole graph, it's the highest point. That's for the maximum, right? So then if it's a maximum, or if it's a minimum absolute, or if it's an absolute minimum, that means it's within the whole graph. It's what? It's the lowest point. Maximum means high, minimum means low, like we said here, low, high. Now relative, this is where it might get a little confusing, or a local. Relative and local mean the same. What this means is in a general area, these are local mins or local maxes or relative mins or relative maxes. Okay, so now let's go to the graph and kind of talk about these a little bit. If I see here, hills and valleys, okay, we got kind of a valley going on right here, right? This is like Death Valley, okay, where it's really, really hot. And then I'm going to come to a mountain here, and I got the Rockies, and now we're really tall. Oh, and then we're coming back down, and I got some other low point on Earth, you know, and so on. We're just going through. So what I want to do is I want to label all of these mins, maxes, absolutes, relatives, and stuff like that. But if I look here, at the top of this hill, this is a maximum because it's up, right? It's at the top of a hill. So maximum means top of hills. And minimums, we can say bottom of hills or bottom of valleys. But whatever you want to do, as long as you get it correct and you understand what's going on. So this is a maximum, but what type of maximum? Well, if I look at this, this is actually lower than this one, right? So this is lower, so this is a local max or a relative max, okay, or a relative max there. Well, what about this one here? This is at the bottom of a hill or the bottom of a valley there, okay? Well, if I look, though, this is lower than this one, which is lower than that one. So this is the lowest, which really doesn't matter, but that means it's just a local max. I'm sorry, a local min or a relative min. Whichever way you want to write it, it doesn't matter, it's the same thing. What about this one? This is another bottom of a hill. Okay? If I look, is there any point lower than this point on the graph? Well, there's not, because this low point is actually higher, and then this low point is actually higher. So this is a minimum, but this is what we call an absolute minimum. That means that the graph is lowest point is right here. There is no lower point than right there. That's why it's an absolute minimum. So what I want you guys to do is to try these two. So this one right here and this one right over here. I want you guys to see what they are. All right, this top one right here, we call this one a relative max or a local max. And some of you are like, why is it a relative and not an absolute? Well, that's a very good question, so we need to understand this. If I look at the ends of the graph, the arrows here, these arrows tell me what? That it goes up and up and up and up and up. Well, that means that there is no absolute maximum, because these endpoints, or these end lines, the end behavior over here, we'll get to that in a little bit, these go up and up and up and up to positive infinity as high as it goes, as high as it wants to go. So it always can go higher. If I pick a number, it always go higher. So that's why this is a relative, because this is not the biggest point, the highest value on the graph. Well, what is this here? This is, again, a local min or a relative min, because this is higher than the absolute, right? So the absolute's always the smallest value or the biggest value, and then the local is kind of in the area. All right? Now here, where crosses the x-axis? Remember, this is also called x-intercepts. Well, what are these? These are called zeros, right? Or we call them roots. Or remember, we call them solutions as well, right? So we call them zeros or roots or solutions because that is the value at which makes the equation zero, or the function zero. So what are they? Well, those are these particular values here. So that would be like right there, right there, right there, right there, right there, and right there. I know I'm using yellow, but you should be able to figure it out. You got 6 of them. That means this graph would be the equation of something to the 6th power. Remember, x to the 6th power, okay, means I have 6 roots or 6 zeros, x-intercept solutions. So that would be something to the 6th power. And you can see how it does its all little funny going up and down and up and down and up and down. Okay, now let's get to some end behavior because this is going to be awesome and interesting. Okay, let's get to some end behavior. Before we get into some of these boxes over here, I want to kind of refer your attention to right over here. So this is kind of an example of what end behavior looks like. So end behavior, we talked about this is the edge of the graph, and behavior is what it does. So what happens on the ends. That's what end behavior is. So where are my ends? My ends are somewhere over here and somewhere over here. That's the edge of the graph, okay, that we can see on the actual corner or the grid line or, you know, the graph there. That's what we can see. Now, what actually happens when we get there? How do we write it? How do we do stuff? And so on. So this is what happens. End behavior is going to look like this. That's how our answers are going to look. How do I do that? Why does that not make sense? And so on. And we're going to hopefully try to alleviate some of those questions. So end behavior basically says as x approaches negative infinity and x approaches positive infinity. If I look here, that's what it says right there, the top line of those two boxes. What I need to do is find out what happens when x goes negatively or x goes positively. Okay? Remember f of x, yes, it's the function name, but remember another name for f of x is just the letter y. Remember, f of x is y. Basically, it says, if I plug in x to the problem, what do I get out? And that's what f of x is. If I plug x in, what do I get out? And what do we get out as y? Remember, input-output tables from, I don't know, way back in junior high. So what happens? If I look at this graph, where is x going negatively? X is going negatively when I go to the left from the origin. Okay? It's going this way. That's negative x. So negative x's. Right? That's x goes negatively. Well, what happens to the y number? Well, y is going down here. So at -1, it's there. At -2, it's down here. At -3, it's probably down here somewhere. So where does y go when x approaches negative infinity? Well, y, remember f of x equals y, so y approaches then negative infinity because it goes down, right? It goes down. It's below this x-intercept right there, okay, x-axis right there. So that's the one part of it. Well, now this end behavior here. Well, in this case, x is going positively, right? Positive, right? It's approaching positive infinity. So what happens? Well, guess what? It's still going down. So as x approaches infinity, or the highest number you can think of, that means f of x also approaches negative infinity. Because it goes down, no matter what x you put in, it's going to go down. It's going to become a negative number. So that's all end behavior is just looking at the actual edges of the graph and seeing where they go. Do they go above or below the x-axis? If they go below, then it then approaches negative infinity. If it goes above, then it's going to approach positive infinity. Okay, now this, remember we talked about this as a polynomial right here. This is what this actual function is. It looks like a W. Let me kind of erase this here and kind of see what we got here. So remember, this looks like a W. It kind of looks like somebody sat on it right here. You know, I sat on it because, you know, it's not very high. So, but this is what it looks like. And there's a couple things we need to know, and that's what we're going to get to here in a little bit. But I'm just letting you know this is what it is. And maybe you can kind of see some similarities and some differences as well. But what I want to do is I want to go through one more example of kind of end behavior here underneath this actual graph, the smaller one there. So let's see what we got. So this one here I'm going to say is f of x equals x squared minus x to the 7. Now what I want to do is I want to do a little rough sketch. Now a rough sketch is just a sketch of the graph that looks similar. I'm not saying it's going to be exactly correct, but it's going to look similar. So here's my graph, and if I notice, this is not in standard form, but now this, sorry, this should be negative x to the 7, plus x squared is now in standard form. This 7 is going to tell me something. So that 7, it's odd, okay? And with odd degrees, the leading degree, leading coefficient there, leading term, they tell me something. Because it's odd, it's going to look kind of like a sideways S. It's going to look like this or like this. Yeah, so this negative is also going to tell me something. This means that it ends negative. It's going to start off positive, and then it's going to end negatively. So the rough sketch of this kind of graph is going to look something like that. Now, it's not going to look exactly like that, but again, a rough sketch means it doesn't have to look exactly like it. It can be kind of a rough sketch, like a rough draft, right? That's not your final draft. There's other things that we have to do to make it look kind of pretty. So this is, again, a rough sketch. So what do? I want to find end behavior. So where the edges, the ends of the graph, I want to find out where they go. So this side here, as x is approaching negative infinity means it's getting smaller, like -1, -2, -3, ... negative infinity here. What happens to my graph? Well, it goes up and up and up and up. Well, what does that mean in terms of infinities? That means that f of x is approaching positive infinity because it's going up and up and up and up and up and up and up. So in this case, as x approaches positive infinity, meaning it's going up and up and up, so 1, 2, 3, ... positive infinity, what is happening to the graph? It's getting smaller and smaller and smaller and smaller and smaller. So as x approaches positive infinity, right, we said it right here, what happens to f of x, or actually the function? What happens to the function, the y value? That means f of x approaches negative infinity. So end behavior, all what happens is you just want to find out what happens at the edge of the graph, right? So let's look at these actual kind of diagrams here and kind of talk about them. So this graph basically tells you exactly what we did on this one and then the other one that I did on the other side there. It says that if I have an even power, means if I have an x squared or an x to the 4 or an x to the 6 or an x to the 8 or x to the 2n. 2n means an even number, right? 2 times any number makes an even. So what's going to happen is if I get an even power and a positive constant or a positive leading coefficient, that means, can't spell there, but coefficient, that means that if I have a positive 1 or 2 or 3 or 4 or 5, it's always going to go up. Okay, remember we had an x squared and that looked like a u, and an x to the 4 is going to kind of look like a little w. Okay, it's going to look like that. Now it could be kind of short and fat, or tall and skinny, or one side's short, one side's fat. Stuff like that. It all depends on the actual values of these numbers here, but that's the general shape of that graph. With an odd power, this would mean x to the 1 or x to the 3, x to the 5, x to the 7. You'll notice that the graph starts in one direction and ends in the other. Over here it starts high and ends high, or we'll go down here, but I don't want to do that yet, but it starts low and ends low. So it's in odd powers, it starts on one side and ends in the other. Okay, and it kind of looks like a sideways S. And again, with higher powers, it's going to look a little different, but that's what's going to happen. So this is what's happening with the end behavior. As x approaches negative infinity, let me erase that stuff for you up here. As x approaches negative infinity, that means it's going this way, right? There. What's happening to my y value, or my f of x? It's going up. You can see the difference. My arrow is pointing up, so it's going up. Well, where is up? Up is positive infinity. And the same thing over here. As it gets bigger, x, what happens to my y? It goes up and up and up and up. Therefore, it gets positive infinity as well. Over here, what happens? Well, if x is getting smaller and smaller and smaller and smaller, that means y, in this case, is getting smaller and smaller and smaller and smaller. And then if x is getting bigger and bigger and bigger and bigger, what happens to my y value? It gets bigger and bigger and bigger and bigger as well. So that's where I get those from. And you can see the difference between negative constants as well. So again, that's x squared, x to the 4th power. If I have a negative 1 in front, it basically takes the graph and it flips it. It reflects it. That's what it does. Same thing here. Well, if it's reflecting it, what does that mean? That means my end behavior is going to be opposite. So when the leading coefficient is negative, that means the graph is basically flipping from where it was up here, all right? And my end behavior changes, and we have to look at the end behavior. Because when x gets bigger and bigger, this gets smaller and smaller and smaller and smaller. As x gets smaller and smaller, y gets smaller and smaller and smaller and smaller. And the same thing over here. Gets bigger and bigger and bigger, smaller and smaller and smaller. That's how I get positive and negative infinity right there. Okay, that's end behavior. Now let's move on. All right, here we got some examples. What I want to do is, according to its end behavior, I want to match the graph. So if I look at this one here, the leading coefficient is a 1 and the degree is a 3. That means that my graph is going to look like this, one of these. So let's go up top here and see what we got from these boxes. So that was an odd power right here. It was an odd power, so it's in this category. But the leading coefficient was positive. So we know that it's going to look like this. Okay, it's going to look like that. So let's go down and see what we got there. Which ones start low and end high? Well, this is the only one right there. So that is going to be letter C. Or this is going to be number 1, right? So let's go to number 2. Again, I have an odd degree and a leading coefficient of a negative. So what that means is I'm going to take what I had here when it was a positive 1 and it's flipping it. So instead of starting low, end high, it starts high and then ends low. So that's why this one has to be letter B for there. And then number 3 looks a little complicated, but in reality it's actually pretty simple, and this is how it's really going to be easy to graph equations using this particular method here. Well, what do I know about this 2 in this binomial? Well, this means that I have x plus 3 twice, right? And then I have x plus 1 twice. So what does that mean? That means that how many x's do I actually have? 1, 2, 3, 4 x's. So if I have an x to the 4th power, that means it's even. That means it looks like some sort of W, right? From above, we talked about that. So a W looks like this. But what do we know about the leading coefficient? The leading coefficient is negative, so that means this graph actually flips. So it's going to look something like that. Now, again, it's not going to look all like that, but it's going to look something like that. Well, where does that go? That goes to A because it looks like a W. Now, something else here that we can talk about. Remember from previous sections, this here means that this is in factored form. Can't I solve an equation or find the zeros of a factored binomial or factored polynomial here? So this makes a negative 3 and this makes a negative 1. Those are my zeros. Well, this is negative 3 and this is negative 1. We'll learn how to do zeros here in a little bit, but that's what we're doing. Let's move on to the next page. Okay, let's get into the last couple examples here of this section. This particular example here, we're going to need to use a calculator, and the graphic calculator that you have is that Wabbit one. I'll show you how to use it, how to make sure we can do this whole problem using a calculator, make sure the steps you use, the buttons to press, things like that, so we can kind of make sure we get the right answers all the time. Let's look at this particular function. We have f of x is equal to x plus 1 times x minus 2 squared. And what I want to do is I want to write it in standard form. And it's actually going to be f of x is equal to x to the 3rd power minus 3x squared plus 4. Now, how did you get that? Well, this x minus 2 squared actually gets put into a box, a 2 by 2 box, and you get x squared minus 4x plus 4 for that particular area. And then you put that trinomial and this binomial into another box, okay, and multiply through and combine terms. And this is what you get. So just take my word for it. This is what you get. I don't want to go through how to do this. That was a different section. And you can do that on your own. So what I want to do, a couple things, is I want to graph the function. I want to label all extrema, zeros, intercepts, and end behavior. Okay, and then round to the nearest hundredth if necessary. So I don't know if this one will need to round to the nearest hundredth because I think it'll work out pretty nice. But on subsequent problems, you will need to round to the nearest hundredth if you get to different numbers and they're not perfect numbers or nice numbers. So what we want to do first is I want to take this function. Okay, I'm going to graph it using a graphing calculator. So again, follow the steps that I'm doing. I'm going to show you how to get a table from the calculator instead of plugging, say, -3 in. If I plug -3 in, I get another number out. Instead of doing that manually, I'll show you how the calculator helps do all that for you. Let's get to it. Okay, so this calculator here is the Wabbit calculator. This is the one that you guys got on your desktop of your computers, whether it be in school or at home. You can easily put it there. If you have questions on how to actually install it or whatever, let me know, and I'll walk you through the process in class. Okay. But so you should have this popped up. You're going to need this calculator for this whole problem and for the next one as well. And I'm going to show you kind of all the steps on how to kind of do this problem on this graphing calculator. It's a graphing calculator for a reason. Talk about graphing and all that stuff. So what we're going to do is we're going to first turn it on. So then let me do something else actually. Let's view some key press history. Okay, let me clear this here. What this is this going to show me what I'm pressing here. Okay, and so it'll pop up, but it'll also show you. So if you're having trouble keeping along and trying to maintain your I guess a level of knowledge here, this key press will show you what I'm actually pressing. So if I press 4 plus 6, that's 10, but if I hit enter, that gives me 10 on the calculator, but 4 plus 6 equals, again, that's how this is what it's going to look like. So let's get to what I got to get to. So let's get to graphing this here, x to the third minus 3x squared plus 4 on this calculator. So you notice in the top left-hand corner you have a y equals button. What you're going to do is you're going to press that button. It brings up a whole bunch of different y sub 1, y sub 2, y sub 3. Those are a bunch of equations that you can graph on this. You can graph 7. You can actually graph more than that, but right now it's showing 7 here. So what I'm going to do is I'm going to type in x to the third minus 3x squared plus 4. So here's what you're going to do. This button here that says x, t, and it looks like a 0 with a circle with a line through it. That's what we call theta. That's that's different higher level mathematics. And we have this letter n. Okay, you're going to press this button, and it's going to type in an x. So you can see that up here. Then I need to raise it to the third power. So I'm going to raise, that's a caret button, to the third power. Okay, so now I got x to the third minus, what do I need? I need 3, and then come back up here, that's the x, and that's a squared. You have two different ways you can do it. One is if you look, there's an actual squared button here, x to the square. You can press that, and it pops up as an x squared. If you didn't know that there was an x squared button, you could raise it, the caret button, and the 2 power, that's fine. And then plus 4. What I like to do is I like to hit enter afterwards just to kind of make sure it's in the calculator, just so instead of a calculator misreading it. If I look at the y sub 1, there's kind of a blacked out equal sign. That means that that is the equation that this calculator is going to graph. How do I graph it? Well, let's look at it. What I'm going to do is I'm going to hit this graph button on the top right. It says graph, so I'm going to hit it. Now if it kind of does its calculation, now, oh man, that's pretty awesome. That graph right there is the actual graph of what your equation is on the top right up here, f of x and x to the third minus 3x squared plus 4. That's what that's going to look like. But first I said I want to what? I want to fill out a table. So fill out table. Well, how do I do that on this calculator? If I look above the word graph, it says table in blue. Well, that blue tells me I'm going to hit this button second in order to access that menu. So if I hit second and then that button graph, it brings me to a table. Now I don't want to go to 6, that's kind of dumb. So what we do is let's click up and let's go to -3. Okay, so let's start at -3 there. So if I look, -3 is -50. So I'm going to plug in the table starting at -3. I get -50. Let's go to -2. What do I get? If I plug in -2, what do I get out? I get -16. I want you to fill the table up from there. If you need to scroll down to access the next number in line, please do that. But fill the table out and then hit play. Okay, that's what your table should look like. -3, -50, -2, -16, and so on all the way down to +3, 4. You notice that -3, -50, and -2, -16, those numbers are not going to fit on the graph. That's okay, it doesn't necessarily matter. We just need to know where it's coming from and where it ends. And we can see that the other numbers will actually fit on the graph. What I want to do is I kind of want to rough sketch. Second part here is I'm going to go to sketch a rough graph. I can't spell. Okay, what do I mean by that? Sketching a rough graph is we're just going to kind of plot some points here, and then we're going to kind of just roughly sketch it. Remember, if you're in English class, a rough draft is kind of something that it needs fine-tuning. Okay, so we're going to sketch this graph roughly, so it's going to need some fine-tuning down the road. Not necessarily right now, but it's going to need some fine-tuning. So let's use these points to sketch a graph here. I'll leave the calculator up, but I'll take away the key press history there. So what do I get? -3, -50. There's no way I can graph that, right? -2, -16, I can't do that. What about -1, 0? Well, at the origin, go over -1, there's your 0. 0, 4, so 0, 4 is up here. 1, 2 is there, 2, 0 is here, and then 3, 4 is up there. But if I look at the graph from here, what do I notice? I notice that it starts low, comes back down, and then goes back up top. So let's kind of use this same kind of model as our model here. Okay, so we know these are the points that it's going to pass through. So let's look at the graph here. I know that it's going to start from down and go up, and it's going to kind of turn, and then it's going to turn again, and it's going to continue going up. So let's use that to our ability as best as we can. We know that this right here is going to turn, and it's going to turn there, right? And then this here is going to kind of come right down there. So this is kind of a rough sketch. Again, we don't know all the points. We just know some very easy ones to graph. So this is your sketch of this particular graph here. So graphing the function, boom, right there, that's done. Okay. Label all extrema, zeros, intercepts, and end behavior. Well, I'm going to show you how the calculator will calculate extrema, zeros, and intercepts. Okay, I know you can probably calculate it as well because these are easy numbers to use, but if we get to some numbers where it's decimals, you can't just blindly say, oh, it looks like that. Okay, we can't do that. So what we're going to do is this here, it's kind of hard to tell how close something is to a specific number. So what we're going to do is we're going to zoom. Okay, if you look at the button in the middle, top middle, it says zoom. Oh man, how handy dandy is that? It's like a handy dandy notebook from Blue's Clues. Okay, so let's zoom here. What I'm going to do is I'm going to zoom box, Z box in the top one, number 1, Z box. I'm going to hit the number 1 there. Now, what Z box basically does is it's going to make a box and it's going to zoom in what box you make. So what I want to do is I want to make a box kind of around this little area here. What I mean by that is I want to kind of make a box that looks like this, because that's really what I care about. This I don't necessarily care about, and this I don't care about necessarily. I care about what's inside, because that's where all the extrema, zeros, intercepts, and all that stuff are going to be. So let's make a zoom box that looks like that. Okay, so here's how we do it. Okay, so zoom box, all right. What I'm going to do is, it's kind of, if you look in the middle of the origin, it's actually blinking. So if I move left a little bit, you can see something moving. Okay, so I'm going to move kind of like right in there. You see that it's kind of above that little hump there? Okay, I'm going to move right in there. I'm going to hit enter. Then, now it looks like it's like a little square. I'm going to kind of move to right in this little area over here. So I just keep going and then keep going this way. Now you can see that it covers all of my points, right? So all of the thing in here, all of the extrema, zeros, and intercepts, it covers it all. Everything on the outside, it's okay. It's going to leave that blank. Once I have this, I'm going to hit enter. Boom. And now you got your little box and where you zoomed at. So now it's a little easier to tell. Now, what are my extrema? Remember, extrema are local mins, local max, absolute mins, absolute maxes, stuff like that. So this right here, what is this? This is a max because it's kind of like on the top of a hill. We talked about that, right? So this is a max. What kind of max is this? Well, this is a relative or a local max because this isn't the highest point of the graph. Remember, this graph keeps going up and up and up and up and up. Therefore, this is the highest. It's just a relative one or a local one. So now what I want to do is I want to find that point. Okay, I want to find that point of intersection. According to the graph, it looks like it's 1, 2, 3, 4, but don't take your word for it or don't take what the graph looks like. Let's make sure we calculate it correctly. So let's figure out how to do that. All right, let's go back to the calculator here. And calculator is used to calculate, right? So look at the trace button and look right above it. Look, it says calc. What? Well, I'm going to use that button there, calc, to calculate some certain values. So here we go. Again, calc is in blue. So I'm going to hit second and then the trace, and that brings up some calculations. What actually happens here? What I'm going to use is I'm going to use some different things here. I'm going to some zero. Look at that. Oh, there's a zero there. There's a minimum. There's a maximum. There's an intercept. I'm going to use maximum. Why am I going to use a maximum? Because we know that this point is a maximum. Right here, we know it's a maximum, so I'm going to use maximum. So I'm going to hit 4. Now, if you look at the instructions on the calculator, it says left bound. What that means is you're going to take your left hand kind of directional pad here, right, your left hand arrow,
I'm going to kind of hover to where it looks like that is, and then I'm going to click about 5 more times. 3, 4, 5. And you can see it's to the left, okay, of that. Now, we can't necessarily say I got to go to the left of it, because when we get to the zeros down here, it's going to look like it's below. But what you're going to do is you're going to basically hover over the point that you think it is, and you're going to just click left a couple times, because I can even go further down. It doesn't matter. So then I hit enter. Then I need right bound. So then you're going to go to where you think that point is again. So we think the point is here, and then I'm going to go to the right a couple times. I'm going to click that right button. So then then you hit enter again. So if I hit enter twice, you'll see that you have 2 arrows. It's going to find the maximum value in between those 2 arrows. Then you're going to let your calculator guess. It's like guess question mark. Then you're going to hit enter again, and then you can see that it puts a point right there. Okay, it puts a point right there. Well, what does that mean? Our maximum is 4. Okay, our maximum is 4. That's what it tells us. Well, now it also says x is negative 1.577 e to the negative 7 power. Well, what the heck does that mean? That means that this is such a small number, the calculator is misreading your actual problem because of some rounding errors. Okay, so it's reading this as like a negative 0.15 and so on to the e to the negative 7. But it's actually, this should be a 0. It's so small because of the rounding errors that this should just be a 0. Well, 0, 4 is our maximum. Okay, so what I'm going to do is I'm going to come up here to this point, and this point is actually 0, 4. And I'm just going to kind of mark it 0, 4. And right here, right from here, that's our max as well. It has it for us already. Now what I'm going to do is I'm going to find this. Well, what is this? Okay, what is this? This is a relative what? A relative min or a local min. You can either use one of either, doesn't matter. So now I'm going to go back to my calculator. I'm going to hit second calc again. I want to find a minimum, so I'm going to choose 3. Again, I'm going to go hover over the dot. So let's go over the dot. You can see the kind of spider is moving its way across the graph. So this is where I think it is. I'm going to hit left 5 times, 6 times, whatever. Then I'm going to hit enter. Then I'm going to hover over it again, and then I'll move to the right about 5 or 6 times. Hit enter, and now it's asking you to guess. Hit enter, and now it's calculating what it calculates. So now if you look at this particular x and y, this is, remember, your ordered pair x comma y, right? X is 2.0000009. Well, again, because of rounding, doesn't this look very close to 2? And that's what we're going to look at. Okay, because of rounding, the calculator is going to say that it's not exactly 2, but it really is exactly 2. So we know that this point here is 2 comma what? Well, this is 2.4 e to the negative 12. That means that's a very, very, very small number. It's 0.11. It's the number point, and then you got 11 zeros, and then number 24. So it's 0.0000000024. Okay, but again, that's very small as well. Again, because of rounding, the calculator is misconstruing this as a number, but it should be a 0. And guess what? 20 is right here. This was our minimum. So that's how we find relative max and relative min. Okay, so here we go. Now, what else do I need? I need to find this 0 here, because a 0, remember, it crosses the x-axis right there. So now how do I find a 0 on this particular graph? Again, I'm going to go back up to second, calculate it, go to the 0 right here, which is 2. I want to hover over where I think that 0 is. So I hovered over where I think that 0 is, and I'm going to go a couple clicks to the left, and then I'm going to hit enter, and then I'm going to go hover over the 0, which is right there, right in this area, and then I'm going to go a couple clicks to the right. Okay, and that's, again, my arrows are telling me it's somewhere in the middle of that. Then you hit calculator, enter again, and then guess what? Now it's telling you that my 0 is negative 1 comma 0. Okay, so this is another 0 at negative 1 comma 0. So what we do is we have our zeros are negative 1 comma 0, 2 comma 0. You could write them as ordered pairs, or you can write them, remember we talked about in curly brackets, negative 1 comma 2. Both of those are okay. This is the ordered pair. These tell me they're zeros. So then what do? We have a relative max at 0, 4. You could either leave it on the graph or you can write it relative max 0, 4, relative min 2, 0. All right. So what do I have? I have extrema right there, relative max, relative min. Zeros, I got them both right here. Intercepts, well, my relative max here just happened to be an intercept. Okay. So we know that my intercept, my y-intercept is 0, 4, and my end behavior, I need to know this. Okay, I need to write it down. So end behavior, remember, as x approaches negative infinity, what does f of x do? And then as x approaches positive infinity, what does f of x do? Well, x approaches negative infinity. I'm going, let me change colors here. I'm going to the left when x approaches negative infinity. Left, right? These numbers are smaller. Well, what happens to my actual graph? That gets smaller and smaller and smaller. So that approaches negative infinity. Well, what happens when x approaches positive infinity? That means my number's getting bigger and bigger and bigger. What happens to my graph? It gets bigger and bigger and bigger. So therefore, f of x approaches positive infinity. So what we did was we graphed the function using the graphing calculator. We labeled all extrema, relative mins, relative maxes. We didn't have any absolutes because they're not the smallest value on a graph or the highest value on a graph. There's always something bigger. That's what these arrows tell you. There's always something bigger or smaller. Zeros, we labeled them. We also wrote them out. You need to write them out as well. Intercepts, we wrote it out right here. End behavior, we finished that up there. And we filled out our t-chart. Okay, so what you guys are going to do is you're going to try the one below it. Use your calculator. Try to calculate all that stuff. Round to the nearest hundredth if necessary. Okay, before you go on to this actual problem here, what I want you to do is look at your window. So if I look at the second button to the right on the very top, you'll see a window. Okay, I want you to click that and you should have something that looks like this. So in the last problem, remember we used Z-box or the zoom box to kind of zoom in using a particular box region that we made. And in this case, what I want to do is I want to fix it. You'll still use your Z-box when you do the problem, but I want this problem to look a little nicer when you graph it before we get to the Z-box. So a standard window, this is what it's going to look like, and I'm going to show you how to fill in and what numbers should look like when in a standard window. So x min, that means what's the minimum point on your x-axis that you want visible. So this is -1, -2, -3, -4, -5. Usually the standard one is -10. Okay, -10. X max is the biggest value of x on your graph. So usually that is 10 as well. Okay, this SCL, X SCL, it's X scale. What that means is, what do you want your increments to be? Do you want them to be 1 or 2 or 3? Usually the standard is 1. When we get really large numbers and real world problems or whatever it is, you might want your scale to be 20 or 30 or 50 or even 2. But 1 is usually what we're using when we graph kind of these, because most of these equations that we're going to graph, functions, are going to be around the origin. So we always want to use the scale of 1. Y min, well, our Y min there is also going to be a -10. That's the standard window, the standard operating window there. Okay, Y max is going to be also, that's going to be 10. That's the highest value that you'll probably use. Y scale is also going to be 1. And then X resolution, don't necessarily worry about that. That should always be 1. Okay, always be 1. So let's enter that. So this is what I have. Okay, this should be your window for everything that is a generic function. This is the starting window. If you graph a function and it doesn't appear in your window, then we need to reevaluate this window or look at your graph or look at your equation, make sure you graphed it correctly. But we need to make sure this is the standard window, and then we can change it from there. Okay, go ahead and move on. Go ahead and try this problem here, and then hit play. Okay, so you see that I have the table filled out. I have the graph, kind of a rough sketch here. I have some zeros that are circled. We got to find the values of those. Same thing with the local mins, local maxes, and this is an absolute minimum. This is the lowest point on a graph. That's why this is an absolute, not a local. Locals are in the area that is min or max. So this is in the area. This is a local max because this goes up and up and up forever. This is a local min because it's bigger than this absolute minimum here. So let's find the actual values. Remember, let's go use our calculator. Remember, this is what the graph looks like. Okay, this is what the graph looks like. So remember, let's go to zoom. Let's use zoom box. All right, let's go scroll over to where we actually need stuff here. So let's kind of go in there, hit enter, and then let's go below the absolute minimum, and then kind of scroll over till I get that other 0 in my way. Okay, so there we go. There's our box. Let's hit enter, and now it's zoomed in to show the 0 that's over here. It's zoomed in to show another 0 that's over here, which I didn't circle over here, which I probably should have, to another 0 here. It's zoomed in to show a minimum, the absolute minimum, and then we have the maximum here, right, the local one. So let's find all these different values of these things using the calculator, using that calc button. So let's find, let's do minimums first, okay? So let's do that. So minimum number 3 is right there. Remember, I'm going to hover over to where I think the minimum is. So I think the minimum is right around there, right? I'm going to hover over it and scroll to the left, hit enter, kind of come back, hover over it, scroll to the right a couple clicks, hit enter again, and then it gives you a point. Your minimum is this point here. So what I'm going to do is I'm going to write it. Again, rounding to the nearest hundredth. Remember, hundredth is 2 places. So I know this absolute minimum, the value is negative 1.21, comma, negative 5.45. Negative 5.45. So extrema, so here's the absolute min, is negative 1.21, comma, negative 5.45. So that's the absolute min. Now let's go find the local min. Let's go find the local min. Go back to minimum up here. Again, I want to go over and hover over that local minimum, or where I think the minimum is, right? So I think it's right there. So I'm going to go a couple clicks to the left, hover over it again, couple clicks to the right, enter, enter, and now it's calculating right there. So if I look, this is 0.999999795. Well, what is that very close to? That's actually very close to the number 1, okay? Very close to number 1. So 1, negative 1 is our local min. Boom, that's nice. 1, negative 1. So that's our local min. 1, negative 1. Boom. Now let's find our local max right in here. Let's find our local max. So we're going to go back to calculate. Now I want to find a max, so I'm going to go hit number 4. Again, I'm going to hover over to where I think it is. I think it's right here. Hit left a couple times. Enter. Hover over it, hit right a couple times, and hit enter, enter, and I get this. So now let's round it. So this local max is 0.21, comma, 0.20, parentheses, parentheses, right ordered pair. So that means we have a local max is our third extrema, and it is 0.21, comma, 0.20. Y-intercept, y-intercept. So let's look at this graph here. Let's try to identify y-intercept from the graph. So if I look, it kind of looks like it goes through 0, 0, but I'm not quite sure. I don't really know. So what do I know about a y-intercept? What's the x value when I have a y-intercept? What's the x coordinate? Well, in a y-intercept, if you don't remember, a y-intercept, the x coordinate is always 0, and the y coordinate is just whatever that number is. So x is 0. Well, okay, that's interesting. I can go to the calc, and I can find a value. So I'm going to hit that. I want to find the value of y when x is what? X is 0. So I'm going to hit 0. I'm going to type it in. So I get x is 0, y is 0. So that means my origin is the y-intercept. Okay, so the y-intercept is 0, 0. That is the origin. That's weird, and I'll talk about that here in a little bit. I'll explain why. But now what I want to do, okay, I want to calculate my 0. So I have a 0 here. I have a 0 here. Technically, I have a 0 there as well. But I know this 0 is my y-intercept because it goes through 0, 0. So I know my 0 is 0, 0. Now let's calculate the other two using the calculator. Let's go to second calc. Zeros are right there as 2. Remember, we got to hover over where I think the 0 is. Hover over where I think it is. I think it's right in there, so I'm going to go a couple clicks to the left, going to go a couple clicks to the right, hit enter, enter, and I calculate my first 0 as negative 1.75, comma what? It says negative 1 to the negative 12th power. But if it's a 0, what is my y value always going to be? My y value is always going to be 0, so we know that has to be 0, right? Now let's calculate my other 0. It's way over here. Let's go to second calc. Let's calculate my 0. That's number 2. Let's hover over that 0. Okay, so I got to hover over where I think it is. I think it's right in that area. Got to go left a couple times, enter. Go to the right a couple times, hit enter. And then I hit enter again, and it calculates a 0 for me as right there, right there. Well, what is that as an ordered pair? 1.32, comma 0. So my zeros, you can write them as this way, negative 1.75, comma 0, comma 1.32. In your curly brackets, that's okay. Or you can write it as ordered pairs like I did here. Either way is fine. All right, we found, all right, kind of made a little mistake here, so we got to go back and kind of refix this. But if I look here, I actually have a 0 here, I have a 0 here, and I have another 0 here that I need to account for. Right, this crosses the x-axis 4 times. I only did 3. It crosses here. There's another one here that I kind of missed. Okay, and you can even see on your graph it crosses in this little area here. So what I want to do is I want to calculate that. That's my last problem here. So again, I want to calculate my 0. Boom, number 2 there. I want to hover over where I think it is. So I think it's right there. So I'm going to hit left a couple times, enter. I'm going to hit right a couple times from where I thought it was, enter, enter. And then it'll tell me is what it is. It is 0.43, comma 0. So 0.43, comma 0. That's my other 0. Okay, again, it can go in your curly brackets as well. Negative 1.75, 0, 1.32, and then comma 0.43. That is also fine. End behavior. So as x approaches negative infinity, what does f of x do? And as x approaches positive infinity, what does f of x do? Well, if I look, my graph, x is getting smaller going to the left. What happens to my graph? My graph keeps getting bigger, right? So that means f of x approaches positive infinity. And then as x approaches positive infinity here, it gets bigger going this way. What happens to my graph? That gets bigger as well. So that also approaches positive infinity. Okay, there you go. There you got it. That is 4.1 in a nutshell. I know it was a long video because I was showing you guys really how to use a calculator. I'll put more tutorials up for calculator problems and how to use them, things like that. But for the most part, that's pretty much all you need to know on how to use a calculator for this particular unit. As long as you can graph them on a calculator, know how to mess with windows, zoom boxes, and all that different stuff, you are good to go. All right, that concludes this video. All right, take notes, do work, be successful.